Hello and welcome. Today we'll be talking about the concept of tangential and normal components. Reference Beer and Johnson. Vector mechanics were engineers. So, what is a tangential and normal component? Let us plot a simple graph. Here's x and here's y. This is the motion of a particle which is going in a curve. When the particle is at position P at any instant, then its tangential component will go about like this, and let's suppose this is ET. Then it would also have one normal component directed towards the center of this curvilinear motion, which is denoted by vector En. When the particle moves along this curve, it also reaches at point P dash at certain time, and therefore it will have another vector defining it known as Et dash. Now let us try to derive relation for acceleration, velocity for tangential and normal components. First of all, let us use triangle law. We know that Et plus del Et will be equals to Et dash. Let's write it down. From here we can get the relation that del Et will be equals to Et dash minus Et. Let us suppose that the angle between these two vectors is theta, del theta, and for very small limitation between these 2 points, where for a very small instant of time, P and P dash almost fall at the same point. That's how we create this triangle. When del P is equals to 0, that is the difference between these 2 points is almost equals to 0, we have that P dash tends to P, and hence we form this triangle and derive this relation. Now let's move forward to what is Et cap. Et cap is the unit vector tangent to the path of the particle. Let's use this triangle to write this relation. For del theta, we know that for del theta or sine del theta, we know that it would be equal to del Et by Et dash, the hypotenuse component. Similarly, sine del theta by 2 would be equal to del Et by 2 Et dash magnitude. Since the magnitude of the tangential component of the vector is equals to 1, we can simply write sine del theta by 2 is equals to del Et by 2. Let us try to convert this into the form det by d theta is equals to 1. For that, we can take the concept of limit. When limit del theta tends to 0, we know that sine del theta by 2 by del theta by 2 is equals to 1. And when limit del theta tends to 0, we also know that del Et by del theta changes to det by d theta. This is equals to 1. The expression det by d theta has magnitude 1 and is directed towards the center of the motion. This is Et, and this is very small portion here is det by d theta, which is equals to 1. Every det by d theta is directed towards the center and it is in a curvilinear motion. Therefore, we know that when this condition is applied, very small change in tangential component is equal to the normal component of the vector. Let us move forward to deriving the relation for velocity and acceleration for tangential and normal components. The velocity of the particle is tangent to the path, so it can be expressed as the product of scalar v and unit vector Et. Simply, we know that acceleration is equals to dv by dt. Differentiating velocity with respect to time, we get At tangential component plus An normal component of the vector. How do we get this relation? we have to apply the product rule of derivatives here, and we differentiate once with respect to v and second time with respect to et. Therefore, we get velocity and the component of the vector plus component of the vector times derivative of the velocity. We write this here, and we further separate this to get expression for normal component. We have one tangential and we'll have to have one normal component for the acceleration. Therefore, we use chain rule here. That is, dEt by dt is written in the form of dEt by d theta, d theta by ds, ds by dt. When simply using chain rule of derivative, what we can do is d theta by dt can be simply written as d theta by ds times ds by dv times dv by dt. This and this is equivalent. This and this is same. That's what we have simply done here. After that, we can change dEt by d theta to en, which is what we've derived here in the earlier expression. And after this, what we can do is simply write down d theta by ds in the form of 1 by rho. What is this? Let's come to this figure. We know theta is equals to L by R. Here our L is ds and our R radius component is rho. That's what we have simply done here. D theta is equals to ds by rho. Now we know d theta by ds is equals to 1 by rho. Substituting this into our relation, d theta by ds, we get this expression. We can simply write ds by dt as velocity. Now we write dv by dt as acceleration along the tangential component and v square by rho as acceleration towards the normal component. We have v square by rho e to the power n. This is the expression for acceleration for a curvilinear motion having tangential and normal components.